In this presentation, we're going to go through kinematics, the study of motion without regards to forces. And in this specific presentation, I'm going to go through part one, types of motion. And I'm also going to talk about reference frames. We need this framework to be able to go through and describe our movements. All right, so let's start with a definition. I already said it, but here it is: the study of motion without regards to the forces causing motion. So kinematics has the M in it. So if you want to remember that's an easy way to remember this is the study of motion, M for motion. And the first thing we need to do is really define what we mean by motion, or we also use the term movement. Well, movement or motion is from a mechanical definition, or from a perspective from a mechanical world, is a change in space in some time period. Now, and I say in a mechanical world because there's other ways to define movement. In a different world, we could define movement as a way to solve a problem. That is, if we want to get from point A to point B, we need to move. So, but we will go with the mechanical definition of movement, and we'll have some change in space in some time period. In order to quantify that movement, in order to describe that movement in detail, we need a reference frame. And a reference frame is just a way to identify where an object is in space. So if we were in a classroom, I would be able to create a seat map by identifying what seat you sit in based upon the row and the seat number from the aisle. That's just a reference frame. And then I'd have a seat map, and I would know if someone's sitting in row 4, seat 6, that I would be able to identify who that person was on my seat map. Nothing different here, and but we just have a fancy way of referring to this reference frame. We call it a Cartesian coordinate system. And a Cartesian coordinate system is simply three axes, or three reference lines that are at 90 degrees to each other. There's other reference frames in physics. However, we are going to only use the Cartesian coordinate system to describe the location of an object in space at a particular moment in time, and how that object changes its location in space over some time period. So in a Cartesian coordinate system, we have an XYZ axis, and depending on which physics book you pick up or which biomechanics book you pick up, these axes may be ordered in different, or set up in different orders. Frankly, it doesn't matter. There are some ways that we, later on, when we start doing physics, it's nice to have the X on one particular axis, Y on another, and Z on another. But for the most part, it really won't matter. In fact, we will go back and forth between having X as a horizontal, or sometimes X as a vertical. And you'll see why later on in the other presentations. The key with these three axes are that they are 90 degrees to each other. So 90 degrees between the X and the Y, 90 degrees between the Y and the Z, and 90 degrees between the X and the Z. Okay, so each one of these axes provides unique information. And all we do is we identify the location in space relative to these axes. And there's two different types of reference frames that we will need to be familiar with as we go through this course. One is a global or laboratory reference frame. What this means is that the origin, or where the axes intersect, the origin is located within the room. So going back to my seat map, my origin of the seat map would be row 1, seat 1. Okay, that's fixed in space. That is a laboratory or global reference frame. It's not moving, for the sake of our discussion and the way that we're quantifying movement. The same thing, if we go in the laboratory, you will often hear us talk about setting the origin of the global reference frame, the lab reference frame, to a particular location in the lab. And we say this position in the lab is 0, 0, 0. That's where all three axes intersect with each other. It's arbitrary in one sense, but it's the key is that that origin is fixed. It's not moving. And therefore we call that a global or laboratory reference frame. The other reference frame that we'll end up talking about throughout this course is a local reference frame. What this means is that the origin can move, and it moves during the movement, most likely. So for example, I've got this reference frame right here on this person. The origin of the reference frame is the elbow joint. That origin is going to move as this person does their movement. In this case, it's a lacrosse shot. And that origin is not fixed in space. It's going to move. And what we will often do is we'll have this local reference frame in order to describe how one segment is moving relative to another segment. Okay, so that's a local reference frame. We could put in a local reference frame at the knee joint, at the hip joint, wherever joints exist, we can put a local reference frame. There's other ways to put that origin, or there's different ways to, different locations that we can put that origin, and it's going to give us different pieces of information. So a local reference frame is local to a particular set of segments, in this case, the forearm and the upper arm. The laboratory reference frame does not move. The local frame does move. And for our purposes, when we're dealing with human movement, most of the time we're dealing with local frames with the origin at some joint. Okay, so those are the two types of reference frame. All right, and so here's just examples. Oh, and this is also just important to recognize, is here we've set our reference frame, our global reference frame, at one particular location. It's not going to move, and then we'll be able to quantify the objects, in this case, the runner's movement relative to this reference frame. Now, what I am illustrating here in these two pictures is the x-axis is positive in the direction of movement. All right, and so what we can do, and this is the beauty of physics, is we can set the origin somewhere else, and the positive x direction we can also set in the direction of movement, but you can see how we just flipped it relative to this picture here. The key is when we start dealing with reference frames and we try to, we're quantifying position, we need to give the reader or give each other information about what reference frame we're using. All right, now the other part of this presentation, I want to describe types of motion. We talk about three types of motion: linear, angular, and general. So three types of motion. Let's go through each one of these. In linear motion, when we're dealing with linear motion, we have two types of linear motion: rectilinear and curvilinear. Rectilinear is when all points of an object travel the same distance in a straight line. Distance, we need to now define as total change in position. All right, so whatever the distance is, it's the total change in position. So if we track, and I'll show you in just a minute some illustrations. If we track an object from point A to point B, whatever path that object took is the total distance. If you're driving your car, your odometer is telling you the distance that you're driving. It doesn't even matter what direction you're going in, it's measuring how far you're actually changing position. All right. In this case, rectilinear motion is all points travel the same distance, the same total change in position, and it's a special condition where it's on a straight line. Curvilinear motion, so again, we've got linear motion here. Here's the linear part of this word. There it is. Linear portion of this word. All points of an object travel the same linear distance along a curved path. And I'm going to show you that in just a second here in the next slide. So this is not angular motion. I'm going to show you that. This is the one type of motion is linear motion. All points of an object travel the same distance, either in a straight line, rectilinear, or in a curved line, curvilinear. All right, let's look at a couple of illustrations. The top illustration is illustrating rectilinear motion. All points of an object, in this case, what I have here is an object, and then I have that object at different moments in time as that object moves over to this position all the way over here. All right. So from this position over to this position, and these are just different moments in time. And I've tracked two points on this object, this red point and this green point, and then I just connected the dots from each position. And you can see if I pulled out a ruler, this line, the length of that red line, is going to be the exact same length as this green line, meaning both points traveled the same distance, total change in position. And because it's in a straight line, we call that rectilinear motion. The second type, curvilinear motion, is still linear motion. Here's that same object at this moment in time, and then over here at some other moment in time. And then these are intermediate positions at different moments in time. And all I did again is I connected the dots. I don't know why I used the yellow line here. I should still use a red line. And I connected the dots here. And you'll find, if we do this really carefully, these two lines are perfectly parallel to each other. And if we pulled out our ruler, the length of this yellow line will be exactly the length of this green line, meaning it's still linear motion. There's no rotation of this object. This object is maintaining this vertical orientation in our laboratory reference frame. So all points of the object, in this case 2 points, travel the same distance, total change in position, along a curved path, and therefore that's curvilinear motion. All right, the second type of motion, so that's first type. Second type of motion is angular motion, and this is movement of a segment about an axis, or segments. It could be two segments moving. In the case of the human body. We have rotational motion as another way to describe this movement. So here's just a simple illustration, an axis of rotation right here, and I've got some segment rotating from this position all the way over to this position. Again, it could be one segment, it could be two segments, what have you. So kicking the ball, doing some golf swing, those are examples of angular or rotational motion, flexion, extension, internal, external rotations, and so forth. All right. Okay, so that's angular motion. And I've got another presentation to talk about angular position and quantifying that position. That's another separate presentation that I'll have you watch. So the third type of motion is general motion. This is a combination of linear and angular motion. And in general, human movement is general motion. It's a combination of both linear, all points of an object travel the same distance, and angular motion about an axis. And so here, this is an example of a lacrosse shot where this person's in this position here, and they're going to progress in time linearly, and there's going to be lots of angular movement as well. And so that is considered general movement. This is the type of movement we want to be able to understand, and we want to do biomechanical analyses of this type of movement. In order to do that, we actually do we sort of divide our analysis into two analyses. One is a linear analysis, and the second is an angular analysis. And we progress down those two different analyses, and then we take pieces of information from both of those analyses to try to understand general movement. General movement just by itself is very complicated. So we really break that movement down into smaller components. In this case, we break it into the linear component and then the angular component. All right, so quick summary: kinematics, the study of movement, regardless of the forces causing that movement. Movement is a change in space in some time period. We have two types of reference frames that we're going to be talking about: a global or fixed reference frame and a local or a movable reference frame. And we're going to use the Cartesian coordinate system, which is simply X, Y, and Z axes. And then the three types of movement, there are three types of motion: linear, angular, and general. Linear motion, all points of an object travel the same linear distance in a straight line, rectilinear, or in a curved line, curvilinear. Angular motion is motion about an axis, and general motion is a combination of linear and angular. Okay, that's it for this one. Thank you.